Başlattın mı? Thank you for coming, everyone. Today we are here for 2024 Nobel Physics prizes that is going to be given by, the seminar is going to be given by Professor Dr. Sinan Kalkan.
Thank you for the invitation, for the introduction, and for the opportunity to talk about these interesting models. So I had the chance to use these models in our research as well. I'm excited that I'm happy that they have been considered for the Physics Nobel Prize this year. Before talking about these models, I want to first introduce myself. So I'm coming from a different department, probably don't know anything about me, what I do, what I work on, etc. So I'm coming from the computer engineering department. I did my bachelor and master of science degrees in the same department, and I did my PhD in Germany. My main interests are computer vision and the rise of deep learning based approaches. Nowadays we are using deep learning for everything, so in a sense we have developed expertise in deep learning as well. I'm affiliated with many research groups and centers. One of them is the Image Processing Laboratory in our department. It's one of the most established, largest groups working on computer vision problems. So we have many faculty members that are focusing on trying to see whether we can program machines so that they can see and understand the environment through the cameras. I was facilitated with the Cohen Research Lab. In the Cohen Research Lab, we had many different types of robots and we programmed them for different tasks. I contributed to this lab with my background in computer vision and machine learning. Now that lab is expanded, combined with other labs, and it is converted into actually a very large research center. It's a robotics and AI research center, ROMER. It is in the research park building next to Mortimer building. If you saw that large white building, it is in one of the floors in that large building. It's one of the leading research centers in AI and robotics, not only in Turkey, across Europe as well. So we have many labs there. I'm affiliated with the lab focusing on robot perception, learning, and planning. And we have many facilities available in this lab. So if you are into robotics or AI, I strongly recommend you to consider checking out the activities of this center and maybe joining them. So let me briefly talk about some of my research. Some of these are going to be relevant to the models that we are going to talk about. One of them is the problem of context. So we humans are very good at resolving these ambiguities by using prior information. So if you look at, for example, this small image, by just looking at this image without having any context, we cannot understand what that is, what this object is. By providing some context, by providing some region around the object, maybe we can get some idea. This might be a tennis ball, or maybe an egg, or maybe a bird, etc. But it's not very clear. When you provide a bigger context, we can understand, okay, this object is actually not lemon or something else, but it is actually a tennis ball. So this is one of the fundamental problems in computer vision and in AI. So many things that we process, reason about, they are ambiguous, and we should somehow represent context or prior information in such a way that we can actually disambiguate these ambiguities. So we did some work along these lines, and actually here for this problem we used Boltzmann machines, and I will briefly talk about them in detail. So another problem I'm working on is object detection. So in object detection we are interested in recognizing objects in the scenes and placing boxes around them. So we want to, for example, say, okay, there's an object here and it is a person. There's an object here and it is a car. So this is a very fundamental problem in many applications, like for example, autonomous driving. To be able to, for the car to be able to drive, it needs to detect the objects in the environment, locate them, and estimate their labels. So they've been introducing many novel contributions for this problem. Another interesting problem we are working on is that nowadays we are using deep learning, learning-based approaches for solving many different problems, and these approaches are trained, their parameters are obtained by datasets. So we train these models on datasets. So if you look at the existing datasets collected from nature, actually they have a long tail distribution. Right? So the number of samples are not equally distributed over different categories of information. Right? So some objects have more number of samples, some objects have significantly less samples. And if we train these methods based on these data sets, then they are going to perform really well on these classes with significantly a lot of samples compared to samples with less classes with less samples. So we call this imbalance, and in our research we have been focusing on how we can measure this imbalance and how we can mitigate this imbalance. A related concept is bias and fairness in AI. So we are using these models in many different applications, but can we trust them? So one of the issues with these models is that they perform differently across different demographic groups. So on some demographic groups, they make significant errors, more errors compared to some other demographic groups. To be able to rely on these models, to be able to use them in practice, we need to ensure that these models behave same across different demographic groups. They should not have any bias against certain individuals or demographic groups. So this is an ongoing research, this is an active research area. We don't have established solutions, and we have been working on some ideas ourselves in collaboration with the University of Cambridge. So another problem we are working on in ROMAC, Robotics and AI Center, is to make these ugly industrial robot arms and make them more usable and useful for us. Normally, since these robot arms can be very intimidating to work with for human co-workers, we want to extend them, program them such that they are more like an animal, they are alive, right? We add these small movements so that they appear as if they are breathing. We add some objects here like a glass to make them more appealing. And in addition, we program them so that they can learn autonomously to assemble objects on their own. Normally, these instructions for assembling objects are hand designed by an engineer, which can have mistakes, which is a very tedious task. So we want to program them to learn to assemble objects on their own. And once that is done, these robots can follow the task, they assemble the task based on the state of the task. It can fetch the next object that is relevant for the task, they assemble the task, and it can help a human worker as if it is an apprentice. Another problem we have been working on is the use of machine learning for energy. So energy is a very valuable commodity. It is going to be maybe more significant in the near future. And with scarcity in energy resources, stakeholders and decision makers are trying to come up with ways to reduce energy consumption in different sectors. One of the important consumers of energy are actually the buildings we live in, right? So to be able to make intervention at the building levels in residential buildings, like for example, come up with strategies saying that, okay, if there are buildings with insulation value of blah blah for the windows. We want to change those buildings or the windows with better insulations. So this requires actually normally physics-based simulations, which is very tedious, very time-consuming. So we have been showing that we can use actual machine learning for this problem. Given the parameters of the building, we can quickly estimate how much that building uses energy for heating or for cooling, and we can make changes into the parameters of the building. We can change the insulation of the windows, etc. And so we can even calculate how much energy we can save without using any physics-based simulations. Okay, so after this introduction about my background, we can talk about the Nobel Prize. So this was announced in October this month. In this Nobel Prize was awarded to John Hopfield and Geoffrey Hinton for their foundational discoveries and inventions that enable machine learning with artificial neural networks. So this is a bit ambiguous. Let's look at the details. In the details, we see more concrete references to their contributions. So they have selected John Hopfield because of his contributions on associative memory that can store and reconstruct images and other types of patterns in data. We will talk about this in detail. And Geoffrey Hinton for his invention of a method that can autonomously find properties in the data. To look at the details a bit more, John Hopfield introduced a model called John Hopfield network. It uses some ideas from physics that describes actually materials characteristics due to their spins. We will talk about that. This is called the Ising model. So the network as a whole is described in a manner equivalent to the energy in the spin system. So we will see that a Hopfield network has an associated definition of an energy, and based on that energy, we can actually update. We can talk about the state of the system. And when the Hopfield network is fed a distorted or corrupted or incomplete image or the pattern, actually it is able to reconstruct the missing information. So this is a very beautiful concept. So we store some pattern or image in the network. At test time, if something is missing, some of the variables are missing, the pattern is missing, the pattern is corrupted, it is able to recall and complete the missing information or correct the incorrect information. So this is a very beautiful concept in network. And the idea stems from actually the Ising model in physics. And if you look at what Geoffrey Hinton did to earn this prize, he extended Hopfield networks so that it uses more stochastic methods. Again, these are taking inspirations from physics, statistical physics, to be specific. The machine is again trained by feeding patterns, examples that are critical for our problem, and it can be used. It is very flexible. It can be used to classify images, create new examples of the images that we have not seen before, or recall what we have provided. He extended these ideas. He built other types of networks, models, and they were very critical for the development of machine learning, deep learning, and AI. Okay, so in the rest of the talk, I will talk about these models in detail. Of course, I will need to skip some of the details because in this short amount of time, we can only provide a brief overview of what these models are, what they are designed for, what they provide, etc. We will look at Hopfield networks, Boltzmann machines. I will briefly talk about their relevance and importance in machine learning, their relevance in physics. I will briefly talk about the awardees. And there are certain criticisms raised in the machine learning community. I will briefly talk about them as well. If something is not clear at any point, please just ask again. So let's start with Hopfield networks. These are also called associative memories, Ising model in physics. Something is wrong. I don't know. This was introduced in 1982, right? So roughly 42 years ago. So to be able to grasp, better understand what Hopfield networks provide, let's look at the commonly used artificial neural networks in machine learning. So in machine learning, in deep learning, we have these or similar architectures. In these architectures, information flows in one direction. In machine learning or in deep learning, information flows in one way. So we have the input, like for example, the pixels in an image, the intensity of pixels in an image. We multiply them with variable weights. We have these small processing units that we call neurons, artificial neurons. We obtain their values, then we pass them through, again, another layer of learnable parameters, right? We obtain another values of activations through these neurons. Then we have our prediction, whatever we want to predict, whether numbers or class labels. We have the correct values, we calculate the error, and we update the weights in the network such that the error can be minimized. So what is critical here is in the conventional approach, commonly used approach, information flows in one direction. So we cannot say that if this is missing, what is the value for this? It's not possible to recall or reconstruct something that's missing in the network. So whatever the network was trained for, it can predict that, and that only. In Hopfield networks, information flows in both directions. So again, we have neurons. Neurons are connected to each other, so we have full connectivity, and the edges connecting the neurons are bidirectional. So in the case of artificial neural network that I have just shown, information was flowing in one direction. So here information can flow in both directions. So in this basic version of the Hopfield networks, the variables can be binary, either -1 or +1. But there are extensions that address those. I'm not going to talk about them. So the variables can be binary, and each neuron's value can be estimated by looking at its neighboring neurons, the other neurons in the network. We can multiply the values of the other networks with the edge weights, right? We can sum them up based on this sum up quantity by comparing that with a threshold specific to that neuron, which can be 0. In general, it is 0, but it can be non-zero. If this condition is met, we activate that neuron, we set it to 1, otherwise the neuron is set to -1. So we can write this multipart function in a more compact manner. We look at the neighboring neurons, multiply their values, activations by the edge weights, we sum those up and compare that with the threshold, and look at the sign. Now, although this sounds very simplistic, it can do actually very interesting things. So after, let's say, we have somehow calculated these weights for storing a pattern. I will show how we can do that. Once that is done, so let's say we have stored these patterns, so we have calculated these weights such that the network stores these images or patterns. If you corrupt the image and provide the corrupted image on these variables, the pixels, bits in these variables, then and update the states of the neurons using this equation, actually it can recall the pattern it was trained for. We can add noise, we can remove some of the values, set them to 0, for example, or -1, the network is able to reconstruct the missing part or remove the noise. But this is a very nice property. It doesn't matter which ones we are erasing. So we erase some of them, so we add noise to some of them. The network is able to reconstruct the missing information, remove the noise. So this is a very nice property.
So in principle, there should be some limit, right?
Yeah, there is. There is.
So
I'm not going to talk about that, but there is a limit.
do we know some analytical?
Yeah.
Yes.
Yes. There are very nice theoretical analysis on this.
Okay.
So these are some other examples. So when we are learning the weights, it means actually we are storing a pattern, and if we provide an input which is incomplete, that is close to that pattern or in some way, network is able to complete the missing information. We can interpret this from a physical point of view. So if you look at the space of the states, so we have n neurons, n variables in the network, so we have an n-dimensional hyperspace. In this space, storing a pattern means actually that we have a minimum in the space, minimum of an energy function, which we will define. And when you add noise to a pattern or corrupt or erase half of the pattern, actually we are at a point with higher energy. When we are updating the states using the equation I have just shown, actually we are reaching towards a minima where energy is lower. And that minima actually corresponds to the pattern we have stored in the network by learning the weights of the network. We call this an attractor point, and we have a state space. In that space we have an energy function. When we corrupt the patterns, we are somewhere in that energy function, on that energy function. By making small updates into the neurons activations, we are getting close to a minima, an attractor that corresponds to a pattern that we have stored in the network. If we have stored many patterns in the network, in the state space, we have many such attractors, right? So when you put a pattern on the variables with some corruption, with some noise, something similar or dissimilar to what we have stored, the updates take us to one of the attractive points. So there are different ways to update the state. So once you initialize the variables, the neurons, with a pattern, you can update their states, their values, either synchronously, so we freeze all the values in the states, and at once we calculate the updated values and update them at once. Or we can select one unit randomly and update its value, or we can roll a dice for each neuron, and we can let each neuron to probabilistically determine whether it wants to update itself or not. We can try different things in practice, and in general, the second approach is used. But how do we store a pattern? What does it mean to learn a pattern in such a model? Storing a pattern means that when you for the ith neuron, the activation you would calculate should be the ith value of the pattern. So by looking at the other variables, multiplying them with the edge weights, adding them up, I didn't include the threshold for the sake of simplification. If you look at the sign, we should see that this is equal to the pattern. If this is satisfied, then we have stored the pattern. So one solution for this is to set the weights to this quantity. So the weight connecting neuron I and J is actually the pattern value for I and J divided by N. We can easily show why this would work. If you plug in this definition here, you'll see that actually this multiplication is 1, and since it is 1, this would be actually equivalent to P of I, which we wanted to have if you want to store pattern P in the network. If you want to store multiple patterns, that's possible, but there is a limit. So if you want to store k many patterns, you just do the same over k many patterns. We sum them up and divide them here. This is very similar to a learning rule called Hebbian learning. In Hebbian learning, we associate the weight between two neurons by their activations. So if the two neurons, if their activations are aligned, then we have stronger weight, stronger edge connecting them. If their activations are not aligned, we have weaker connection between two neurons. This is commonly used, this Hebbian learning rule is commonly used in different types of architectures. Okay, so here is an example. I will not do all of the derivations in detail. I can share the slides with you. If you get the slides, you can go over the derivation in more detail. So let's say we have two patterns that we want to store, pattern 1 and pattern 2. Let's say we have -1, -1, -1, +1, and here we just have all ones. We can easily calculate the weights using this formula. This will give us actually a matrix like this, connecting, for example, neuron 1 to neuron 1, neuron 1 to neuron 2, etc. So this is a symmetric matrix because the weight edges are bidirectional. So for example, for weight connecting neuron 1 to 2, we can easily see that it's 2 over 4. And then we can provide different patterns on the network to see what it would recall. If you provide this, for example, actually this is one of the patterns we have stored. And if you update the neuron state, you will see that actually it can recall the correct pattern back, which is the same as the input. If you provide a different pattern, so this pattern is actually different than both of them, but it is closer to this second pattern. So when you provide this new pattern, it will recall the second pattern. So when we talk about Hopfield networks, the harmony, the alignment between different states, different neurons, actually is very critical. So based on that, actually, we can update, the updates of neurons are determined. So we can quantify this as a measure, and we can call that as an energy. So we look at the values of the two connected neurons, right? And we can multiply that with the weight connecting them. If the weight is positive, then these neurons should be correlated, and they should be either positive, both of them are positive, or both of them are negative. If that is the case, then we have a high number here, and we have negative sign here, the energy is low. If, on the other hand, we have positive edge here, but one of them is negative, one of them is positive, or vice versa. That means we have positive edge, so they should be correlated, but the activations are in such a way that these current values are negatively correlated. In this case, you have a negative number here, negative, negative, positive, energy is fine. So the harmony of the network can be captured, or disharmony of the network can be captured with this energy measure. You can call this an energy because when you update the state of the neurons, energy doesn't increase. It either stays constant or decreases. So we can easily prove that. I'm not going to do that here. And from this perspective, you can analyze the state space a bit better. You will get state space attractors, actually storing patterns correspond to these attractors with low energy. Any other pattern you provide on the network leads to higher energy, and by updating this state of the neurons, actually we converge to these attractors, which have less energy compared to other configurations. So, to summarize, Hopfield networks are associated with memories. We can store patterns, and once the patterns are stored, we can actually corrupt some of the variables. We can provide only half of the variables, etc. The network is able to reconstruct the missing information and correct noise in our data. It has inspired many different models in machine learning. And I have only presented the basic form. There are stability issues. We need to talk about how many patterns we can store in the network. Robustness is an issue. We can, through a Hopfield network, we can provide a pattern and it can converge to a pattern that does not exist in our patterns that we want to store. So these are issues, and can extend Hopfield networks so that they can store continuously valued patterns. So I have just provided a binary version. So with Hopfield networks, we were able to store patterns, but it had certain limitations. So when we wanted to work with more complex patterns, they were limited. One of the extensions is Boltzmann machines. This is also known as Sherrington-Kirkpatrick model with external field, stochastic Eisen model, or Markov random field. This was proposed in 1983, just a few years after Hopfield networks. One of the limitations of the Hopfield network was that with every update, we can either decrease the energy or the energy stays the same. So in some problems, if you want to, let's say we start here, this is state space, this is the energy, we start here with some pattern, right? What if, and with Hopfield networks, you would actually converge to this point, which might be a local minima, and maybe there is a solution somewhere else in the state space that better represents what we want to recall. So Hopfield network is limited in that regard. So it's very deterministic. It cannot make updates that can increase energy. So to be able to avoid this with our updates, we should be able to actually increase the energy of the system at certain points. So what we can do is we can add noise or randomness to the network such that it is able to, in a controlled manner, is able to make updates that can increase energy at times. So to be able to do that, we first need to talk about the Boltzmann distribution. So this is again taking inspiration from the distribution of particles in physics. So in physics, actually systems follow this distribution. So a system being in a certain state S is actually related to its energy, the energy of that system. So if the energy of the system is high, then actually the probability of being in that state is low. So in physics, in real life, actually systems prefer states that have low energy. So here K is the Boltzmann constant and T is the temperature. So this dependence on temperature is going to be very critical. And the probability that a system will be in a certain state, let's say S of I, is related to the energy of that system, that state, sorry. And this is normalized by the summation of all of the exponents of all other states. So this is very difficult to compute in practice, but in practice, we will, in our derivation, this will be cancelled out. So if you compare Boltzmann machines with Hopfield networks, they are very similar. They have the same energy function. This energy function is exactly the same with Hopfield networks. But there are two differences. One is that updates are going to be stochastic. In Hopfield networks, updates were deterministic and energy only stayed constant or it decreased. In Boltzmann machines, you will be able to make updates that are going to increase energy. So this is going to be very helpful. Maybe another more critical difference is that we have hidden or latent variables now. Here, as drawn in gray, in addition to the visible variables, we have variables whose values we don't know. We estimate them from the patterns we provide to the network. So this energy formulation then uses both the values of the visible variables and the latent or hidden variables. So how can we relate the probability of updating a neuron with the change in energy? So again, note that we want to prefer states with lower energy. But this time, instead of making deterministic updates, we want to calculate a probability. Based on that probability, we want to update the state. So let's say we have a neuron, we want to determine whether we want to change that neuron's value to 1 from 0 or minus 1. So what we can do is we can look at the change in energy. So the energy of the current state of network, if that neuron is 0, and energy of the whole system, if that neuron becomes 1. So we can easily use this equation and do the derivations and do the simplifications and obtain a term here where we have a probability of setting that neuron to 1. We can again do some derivations, get rid of the constant, and we can obtain this simplified function. The probability of setting that neuron to 1 is 1 divided by 1 plus exponent of some quantity. So this is the sigmoid or the logistic function. So this term is dependent on the change in the energy. If this is positive, that means energy is decreasing. If we set that neuron to 1, energy is decreasing, then this becomes a negative quantity. Based on how much the energy is decreasing, this becomes a very small number, and this probability converges to 1. That means if the energy is reduced, then the probability of setting that neuron to 1 is high. If, on the other hand, the energy change is negative, that means energy is increasing, then this is negative, 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 positive, and this would be a high number, and the probability would be very small. So actually we introduced a mechanism now, a measure of probability that is related to the change in energy if it change the value of that neuron. Right, so let's analyze this equation a bit more with respect to the temperature. So now we have a temperature that we can change. If the temperature is 0, that means we have a system that is cooled down. At 0 temperature, if you look at this quantity here, we have something divided by 0, this is infinity, either minus infinity or plus infinity. If this is positive, that means energy is decreasing. If you make the update, then this is negative infinity, right? This exponent converges to 0, 1 divided by 1, the probability converges to 1. Right? So at 0 temperature, the probability of setting that neuron to 1 becomes 1, so and the network behaves like a Hopfield network. If the change in the energy is negative, that means energy is increasing. If we set that neuron to 1, then the probability converges to 0. And it behaves like a deterministic system, like a Hopfield network. If temperature is not 0, we have non-zero temperature, we have high temperature value, then this probability converges to 1 over 2. That means even though the energy might increase, if you make an update on that neuron, the probability for making that update is high enough. So the network can choose to update a neuron's value even if it is increasing its energy. And for different t values, etc., we can analyze the performance as well. And from all of these, we should reason and understand that now by controlling the temperature at high temperature values, we are able to make updates that can increase the energy of the system. But when you cool down the system, when you reduce the temperature and the temperature becomes zero, it behaves like Hopfield networks. It doesn't take actions that will increase the energy of the network. So if you consider the same scenario, two different states, under two different temperatures, a high temperature and low temperature. At high temperature, the thought of moving from here to here or from here to here, they are more or less the same. And note that from B to A, energy will increase, but we have high probability of doing that. When you cool down the system at low temperature, actually the probability from going B to A is now very, very low, and the system behaves like Hopfield networks. It doesn't take this action, it only takes the action which can reduce the energy of the system. So let's look at Boltzmann network with some with two visible variables and two hidden variables. Here, let's say we have these weights connecting the edges and since we have four binary variables, we have 16 different combinations for these states, right? For the visible values and the hidden values. For each, we can calculate the energy of the system. Because we know these weights, we can easily calculate the energy of the system. We can take the exponent of these energies, right? And the probability of being in this state is actually this quantity divided by the summation of all of these. So the summation is 39 something. So if you divide 739 by 39.70, you obtain the probability for the network to be in this state. Then we can calculate the probability of the visible variables as well. So 1, 1. What is the probability of observing 1, 1 in this network? So after learning these weights, what is the probability of observing 1, 1 at the visible variable? So this is a very important measure for us because with this we can reason about the likelihood, the probability of observing a certain state. What is the probability of that system being in this state? In Hopfield networks, we didn't have a probability measure, so we just had an energy measure. We didn't have a probability. So here we can talk about probabilities. So normally when we are training Boltzmann machines, initially every state has equal probability. When we are exploring the space with our updates, we are updating the probability distribution over the states, and in time, over several iterations, it converges to a configuration where the probability distribution doesn't change. We call that thermal equilibrium. So what we generally do when we are training a Boltzmann machine is we start with a high temperature, we gradually decrease the temperature until we reach thermal equilibrium, and at that point, hopefully we converge to a global minimum. This is called simulated annealing. So in a sense, this is very concrete physical analogy. So certain objects at low temperatures, they are very rigid. So you cannot change their shapes, you cannot change their states. When you heat them up, they can actually go to states with higher energy. Without breaking them actually at high temperatures, you can give them shapes, you can change their states, but when you cool them down, you cannot change their shape. So simulated annealing is actually a very related concept. So let me skip those. So here's an example. So we start, this is the state space. We start at the high temperature, we start somewhere random. Normally, Hopf field network, let's say if you start here, it would get stuck at local minima. But with Boltzmann machines, we can take actions, can make updates that can go over energy barriers, we can increase energy, and with that actually we can explore the whole search space more efficiently, and hopefully at the end of the cooling phase we can converge the state that is better. So actually normally we look at energy, so energy is lower, better measure. So here we are looking at the negative of the energy. So how do we train such a network? So Hopf field networks were easier. We calculated the weight by looking at the multiplication of the variables in the pattern. So in Boltzmann machines, that is not going to work because we also have hidden variables now. So how do you determine the values of hidden variables, and how do you learn their weights? And we can talk about two different distributions. Distributions over the training set. So you provide a pattern from your training set on these visible variables. Then you start thermal equivalent. You start at a high temperature, you slowly reduce temperature, you converge to a solution. Right? That is the probability distribution if you provide an example from the training set. And if you randomly provide some values on the visible variables and let the network converge to a solution using simulated annealing, you obtain a different probability distribution. Ideally, you want these probability distributions to be the same if the network is trained properly. When you start with random variables at the visible nodes, it should converge to one of the patterns. And the probability distribution should converge to the probability distribution over the training set, the patterns that you want to store. So we can, since these are probability distributions, we can define a measure that minimizes the difference or the divergence between these probability distributions. Here they use Kullback-Leibler divergence. And G actually depends on the weights in the network. And what we can do is we can determine the weights such that G is minimized. So we have an objective. We are interested in finding the weight that can minimize this objective, so we have an optimization problem. So in 1983, we didn't have backpropagation. Maybe people had already some idea about using gradients to update the weight so that some measures could be minimized. Based on these, they came up with a training strategy. So we have two phases in the network. When we are training the network, we have positive phase. In the positive phase, we provide the visible units with some sample from the training set. And we have negative phase. In negative phase, we just initialize the visible variables with some random numbers. And we can make derivation and come up with this gradient. So the gradient of the objective expected weight is actually equal to the probability between two neurons on the positive phase and the probability between two neurons on the negative phase. And we are actually trying to minimize this gap. So we are trying to increase this such that this probability matches this one. And we are updating the weights iteratively such that this gap is minimized. So this is a very slow process. This is one of the reasons why Boltzmann machines were abandoned. So we need to have loops over the training steps. We need to iterate over each example, training example. We need to, for each example, we need to have a positive phase and negative phase. We need to do annealing. We need to reach thermal equilibrium, etc. So this was computational, very expensive and slow, and we couldn't train Boltzmann machines for practical problems because of it. So this training strategy was very sensitive to annealing schedule, it was very difficult to determine when we reach equilibrium because the state space is too large. And unluckily or luckily, backpropagation was introduced or made more mature in the following years, and the whole literature switched to networks or models that were trained in a feed-forward manner using backpropagation, and they performed significantly better compared to Boltzmann machines, and it was recognized that many problems actually does not need a generative model. So information flow being one direction is actually sufficient for many practical problems. So Boltzmann machines were extended later on to the so-called restricted Boltzmann machines, where connectivity is restricted. So normally you would have connections between the hidden variables as well, between the visible variables as well. So in restricted Boltzmann machines, we just have connections between visible neurons and hidden neurons. So this allowed the network to be trained actually faster. We can train a stack of Boltzmann machines, restricted Boltzmann machines in an iterative manner. So first we train this from the input. We obtain the representation for our inputs with the hidden variables. We use those to train another Boltzmann machine, etc. In this way, in a step, in a layer-wise manner, we can train actually deep stack of restricted Boltzmann machines. So this was called deep belief networks. A similar architecture was developed called deep Boltzmann machine. So the directionality was slightly different in deep Boltzmann machines, but there were a lot of similarities. And despite those extensions, improvements of Boltzmann machines, the dominant architecture nowadays are feed-forward architectures. So let me briefly talk about our work using Boltzmann machines as well. We were using Boltzmann machines for our scene modeling problems in 2017 and 18. And I had a chance to actually explain our work to Hinton himself. So this is from one of the top conferences called NeurIPS. In 2018, we presented our work in one of the workshops. And luckily, Hinton turned up in one of the sessions just next to our poster, and in the break, I just caught him and I briefly explained our work. In the middle, before I could finish explaining our paper, our approach, the next session started and we were interrupted. But at least I had the chance to briefly explain what we were doing. It was very relevant because we were expanding his ideas and showing them they can be useful for some practical problems. So let me briefly talk about what those problems are. So one of the important problems in robotics or in AI is to be able to reason about objects in the scene. So here we have objects are located in the scene, in the environment, with certain special relations between them. So let's say you have a robot helping with you with several tasks at your homes, and let's say there was a party and every object moved around. There are objects that do not belong to your living room, for example, or the robot needs to rearrange the objects such that that clutter, the after party effects are removed. For this to be able to solve this task, the robot needs to reason about what objects should be in that environment, how they should be positioned with respect to each other, whether there's an out of context object present in that environment that should be removed, or maybe there is some missing object in that environment that should be placed in certain special relationship to other objects in the environment. So this is a very suitable problem for Boltzmann machines because we can represent objects as visible variables. We can represent relations as visible variables with one difference. These variables have three edges. Normally, the variables are connected by an edge that connected two variables. So we will have here edges that connect two objects and a relation node. So we introduce the extended Boltzmann machine such that this can be represented, and we know some of these variables. They are either observed in the scene, or maybe something is missing. So we set those variables to off if that object is missing from the scene. We calculate the hidden values, and we calculate back the values for these variables, and based on these, actually, we can easily calculate whether there is something wrong in the scene, whether this should be removed or this should be present in the scene, etc. So this worked actually really well. And it provided us the flexibility to represent the different variables and different relations, and once the model is trained, information can go in any direction. We just provide information here wherever information is available. From those, actually, we reconstruct any other information that is missing in the scene. So this was a very flexible model for us. And then we identified that the number of hidden variables is very critical, and we cannot foresee that in advance. So if you consider a robot can encounter many different types of scenes, many different types of contexts, and somehow the robot in time should be allowed to add more layers or more neurons into its representation or into its Boltzmann machine. So we showed that we can easily do that using a simple mechanism. Hopefully this will work. Yeah. So in time, we provide more scenes, more examples, actually the network updates itself by adding more layers or more neurons so that the scenes can be captured better. So with this, after having talked about these models in detail, so let me quickly talk about their relevance in machine learning. Actually, I have already provided hints about their relevance in machine learning. So there were already some associated memory models before Hopfield networks. But Hopfield networks inspired other models, further research, further methods that provided the same functionality. We have other models, the so-called associated models that were introduced later on. And generative models that are nowadays used for generating new content. In some of those models, we used actually energy-based formulations for generating content, learning and generating content. So these actually take inspirations from Hopfield networks and Boltzmann machines. And Boltzmann machines is extensions like received Boltzmann machines and learning stacks of received Boltzmann machines to better capture information about the scenes, representations of the scenes. Actually, they paved the way for learning representations of the environment, of the problems, for solving different problems in a more easy manner. And for their relevance in physics, I'm not a physicist, so I don't have the background to talk about this much, but actually they take Hopfield networks as directly an implementation of the Ising model in a machine learning problem actually, for storing patterns. Right? The energy formulation that will describe the behavior of particles in an Ising model actually is directly the energy formulation we use in a Hopfield network. Right? The model is directly taken from physics. And the stochastic version is actually the Boltzmann machine. So there are many notions, concepts in physics that are analyzed or represented or investigated using these or similar ideas. That is representations of solids or materials like glass, graphene, etc. We can talk about the Hamiltonian of a system. We can talk about the Hamiltonian of networks as well. So we can quantify the energy of a network, and can make updates in the network, parameters of the network, such that that network goes to a state with lower energy. So let's briefly talk about the recipients of the prize. Let's start with John Hopfield. He was born in 1932, and he took part, actually he witnessed, in a sense, many critical advances in AI and machine learning. So he's a physicist by training, and his PhD was actually on concepts in physics, in quantum mechanical theory of the contribution of excitons to the complex dielectric constant of crystals. I don't have any idea about the rest, but I have a feeling that he's working on Ising models, or he's using Ising models for in his thesis. So, as a physicist, he used Ising model and similar models, and later on, he just extended and applied them to a practical problem in machine learning or pattern recognition, and that worked really well. So, his contribution in 1982 overlapped with the end of the AI winter. So we have several periods of winters in the history of AI. During those winters, people believe that the AI is not going to work, AI fails, we cannot train or design machines, computers that can have AI capability, etc. One of them is this period. So Hopfield networks overlap with the end of the AI winter, and it inspired actually many different architectures, models, and research in AI or machine learning. So he, in addition to Hopfield networks, he worked on its extensions like continuous Hopfield networks, where he relaxed the assumption that the states need to be binary. So now we can work with non-binary patterns. And he has also introduced modern Hopfield networks where we have more capacity to represent more patterns. And he also had concerns about the recent developments in AI. So he said that as a physicist, I'm very unnerved by something which has no control. So he refers to models like ChatGPT being trained on large and large amounts of data, and once you train these models, you don't know what they learn. So you don't have control over what they learn and how they reason, etc. So this is what he refers to. Let's briefly talk about Geoffrey Hinton as well. He's by training computer scientist, cognitive scientist, cognitive psychologist. So he has different degrees in all of these disciplines. So that actually has worked really well in his case. He is he's named as the godfather of deep learning because of his many different contributions. One of them is Boltzmann machines. He didn't invent backpropagation, but he made it more popular. He introduced the well-known AlexNet, which is one of the modern deep networks that worked really well for a practical problem, object recognition problem. And with this study, actually, deep learning exploded, and for every problem, we are nowadays using deep learning. He introduced other architectures like capsule networks, but they were dominated by attention-based networks or transformers. And he also introduced many different concepts that are being used in deep learning. So calling him godfather of deep learning actually is very accurate. And for his contributions in deep learning, he got the Turing Award in computer science, which is like Nobel Prize in computer science. He also raised concerns about the recent advances in AI, and he actually resigned from his role in Google. He had a really important researcher role there, but he resigned from there to be able to freely speak about the risks of AI. So these two pioneers, if we can call them pioneers, they had concerns about the recent developments in AI. Okay, so there were many different criticisms in the machine learning community. I'm sure there are other criticisms in the physics community. I'm not aware of those. I didn't follow that literature. If you have followed that literature, if you want to talk about them, I would be up for hearing about those critics. One of them is from Stephen Grossberg, who is a very well-known figure in machine learning, deep learning. He introduced many different types of architectures, deep architectures, neural network architectures for many different problems. So in this email and list, he criticized the prize, saying that he published articles between 67 and 72 that had the ideas of the Hopfield network. So he had already published similar models, or maybe the same model, earlier. And later on, he says that he published another Lyapunov function. Actually, he refers to the energy function in the Hopfield networks that works similarly, and they have generalizations, etc., but those were not taken into account. And he also criticizes Hinton. Generally, Hinton is linked to backpropagation. Even Hinton himself agrees that he didn't invent backpropagation, but somehow there is this association, so he criticizes that association as well. Schmidt-Huber is another critique of the price. He has been always a critic of the attribution of deep learning to Hinton, Jan LeCun, and Joshua Bengio. Here in his tweet, he said that, okay, these models actually were existing already before, and for the same or similar problems, these architectures, these models were in use and published before. So, in a sense, attributing these ideas to Hopfield actually is inaccurate. So he also criticizes the Boltzmann machine, not citing some of the earlier critical work and other similar criticisms. Despite these criticisms, I believe that Hopfield network and Boltzmann machines were really interesting models. Hopfield and Eaton introduced many other ideas as well, many different models that are being still in use, or they have inspired other models or methods in deep learning, which has actually shaped AI and the state of AI we have nowadays. So therefore, I strongly believe that their ideas, their contributions were very influential, and I'm very positive that their contributions, taking inspirations from physics, are recognized as a Nobel Prize. That is the end of what I want to say. Thank you for listening. Any questions? Yeah.
So, you show some correspondence to these bits, these logical bits to some physical systems, right? You showed some energy function also.
Yeah.
So, is there some corresponding meaning of these hidden variables?
Yeah.
What is it?
It depends on the problem, but in problems related to images, for example, object, let's say we want to design a system that can represent objects. So you provide these pixels as visible variables, and at the hidden node, the hidden variables, actually we observe some patterns that are shared by different objects that we will observe in the images. So we are not providing specific supervision about what they represent, but somehow it learns an internal representation that is shared by different objects. That was very influential in deep learning as well, either in supervised or in self-supervised deep learning, where we try to obtain these useful representations from the data in an autonomous manner as much as possible.
So the visible things are actually the inputs for
Yep.
your
Yep.
system, right?
Yes.
This is the actual physical thing.
Yes. Yes. We
Uh,
provide, for example, pixels,
Uh-huh.
intensities of pixels in an image.
So you just update your deep layers, right?
Yeah.
To understand how can I construct that physical.
Yes, exactly. So the hidden layers then variables represent the information present across different images in a high level, in a more compact space, such that it is able to reconstruct those back. Right? So in a compact space, then it learns these useful pieces of information which corresponds to, for example, some common patterns shared by different objects. So there are visualizations of those. I didn't share them on the Replication file. Okay. Yeah.
So can we just start from, for example, a finite number of inputs, right? Visible
Yeah.
things. So just can we learn that picture, right? So just okay. After that, can we increase the number of visible things and just use the old information from small systems, and we can we enlarge the systems? So just learn.
Yeah. So this is what actually we tried to do in our work as well. So we didn't touch the visible neurons. We just touched the latent variables, but the same can be done on the visible neurons as well. So we can add new visible neuron variables by keeping the existing weights intact. We can, for the new one, we need to add new edges, new weights, and we can update those new edges, new weights.
In that circumstances, we need new inputs as well to train
Yes.
our. Oh,
Otherwise, the network doesn't know what these weights should be, right? It needs samples from which it can learn the weights that can lead to low energy configurations.
So can't it just repeat the pattern? No. Can it
Well,
just
if-
learn by itself?
Well, I mean, for that new visible variable, the value you want to have is the same as other visible variables, maybe you can do something. If you know some prior information, maybe by looking at the weight of those visible variables, you can calculate something, but it's very perfect. Okay, if there are no questions, thank you for listening. Hope to see you in another session.